I'm Arthur Filoche. I recently got a PhD in computer science from Sorbonne University under the supervision of Dominique Berezia. And I'm now postdoc at the University of Western Australia. And I'm presenting today our latest work, data assimilation as variational inference. I've been mainly interested in the intersection of data assimilation and machine learning, and a recent trend seems to train model on reanalysis data, and I'm wondering, will it be possible to train those models directly on observation, and more particularly using physics-based regularizer like in 4D-var? And this got me looking into variational inference. So today's topic will be linking data assimilation and variational inference. And it has been largely inspired by the machine learning community, even though, strictly speaking, what the method I'm presenting is not machine learning, as it can work on one assimilation window like for DVAR. I will start giving the method, then a preliminary case study, and give some perspective. So first, a quick reminder of a classical data assimilation framework. So a system state X evolves over time according to dynamics M. Observation Y are available over time, observed through an observation operator H with an additive noise and potentially some prior knowledge of the initial condition in the form of a background. Now the inverse problem is to recover X observing Y. And to do so, you can use Bayesian modeling framework. And so give a likelihood model and prior model. And if those models are differentiable, well, you can look for estimator by gradient descent, for instance, maximum a posteriori. If you choose to model those errors as Gaussian, well, you end up with the classical least square loss function, with the particularity that it is constrained by the dynamical model. And 4D-var is the algorithm minimizing this loss function. If we look at the computational graph of 4D-var, you see clearly that it's an optimal control problem where the control is the initial condition. So you want to optimize an initial condition that stay close to your prior, but also that produces a trajectory that will fit the observation. But this kind of estimator is a point estimate, right? The algorithm only returns one value. And so this is prone to overfitting, for instance, very noisy data. And also it does not quantify uncertainty. So the question I'm asking is, can we design a 4D-like algorithm overcoming these issues? Now, if we look at what's done in variational inference, ideally we would like to recover the full posterior of X knowing Y, but it's intractable, usually for combinatorial reason. And variational inference tackle this issue by introducing a parameterized approximate of the posterior and estimate the parameter of this posterior minimizing a statistical distance and usually the Kullback-Leibler divergence. And if you look at the expression below, you see that the log evidence appear, and this term is why in the first place the full posterior is intractable. But hopefully this term does not depend on the variational parameter. And minimizing this divergence is equivalent to maximizing the evidence lower bound elbow. And it's worth noting that you can rewrite the elbow in this way. To highlight a classical compromise between a term that want to fit the prior and a term that want to fit the data. And if you want to dig this topic, I really recommend this review from David Blay. That is very informative. Now, how can we apply this in the 4D-var context? Well, if we use the Gaussian modeling, we just have to replace this in the evidence lower bound loss function. And doing so, we end up with this loss function. So this is a simple contribution, but it's the main contribution today. And this loss function is divided into two terms. The first will encourage the variational posterior to place its mass on the maximum a posteriori estimate. And the second one is the negative entropy, will encourage the variational posterior to be diffuse. Now, a quick sanity check. If as a variational posterior, I pick a Dirac distribution or a delta distribution center on the initial condition, well, the entropy term vanishes and the first term becomes the 4D var loss function. So we recover 4D var loss function. So if you have been using 4D var, I would be tempted to argue that you have been using this loss function just with a very tight variational posterior. How do we optimize such loss function? It's not immediate because of the expectation, and particularly the gradient of the expectation does not equal the expectation of the gradient when the distribution depends on the variational parameters. Hopefully, we can mimic what's done in the machine learning literature, and particularly in the paper that introduced variational autoencoder. So reparameterize the posterior and using Monte Carlo estimates and then automatic differentiation. So now if we look at the new computational graph of, let's say, variational inference for dvar, well, we do not optimize anymore on the initial condition, but directly on the variational parameters of the posterior. And there is an additional loss term, which emphasizes the posterior to be diffuse. And again, if you are interested in those topics, I recommend some literature from David Blaise' team. All right, now quickly, a preliminary experiment I did on synthetic data. So using a Lorentz 96 model, using as observation operator the composition of a linear projection and a quadratic nonlinearity and Gaussian errors. So here is an example of simulated trajectory. And you see that we pick diagonal covariance matrix so that we can plot the variance in front of the data, and also the noise at each grid point can have different statistics. And now the goal will be to estimate the full posterior, to estimate the posterior of the initial condition knowing the observation. So let's apply variational inference for dvar with a very simple variational posterior. Let's say a Gaussian, and we also make the mean field approximation, which basically say we are looking for a Gaussian with a diagonal covariance. So now the control parameters are the mean of this Gaussian and the diagonal of the covariance matrix. And those are computationally the same size as the initial condition, same dimension. So we multiply the control parameter by 2. And we use the reparameterization trick exactly as in the variational autoencoder paper. So sampling from a Gaussian and taking the Adamar products to ensure that the variational posterior follow the desired distribution. And the optimization curve looks like this. And so the first thing is that it's not usual, at least for me, to optimize loss function that can be negative, and this is due to the log likelihood term. And also a first potential issue that we can notice is that the number of iteration is very large. So in black, you see the 4D-var optimization. So it's like there is at least an order of magnitude of forward model needed, which is terrible. Now, before looking into the results, let me just introduce a couple of algorithms to compare with. So this one is approximate Bayesian computation, rejection sampling. It's very simple. Sample from the background, compute for the var loss function, and reject if it's above a threshold. So it's very naive, and the idea is kind of a brute force the full posterior, or at least to have a grasp on the ground truth posterior. So here we take 100,000 of sample and we keep 0.1%, and you see that the loss they are around the one we obtain optimizing for the var. even sometime below. And the second one is just an ensemble of 4D var. So perturb the background, perturb the observation, and optimize a new 4D var and create an ensemble this way. So now let's look at the results. So first, the error of the average. The first thing we can see, it's not surprising that if we do not constrain the trajectory with the observation, we obtain big errors. This is represented by the prior. And also we can see that 4D var struggle in some region, and I'm usually calling this overfitting, while the probabilistic method have low errors, at least in the assimilation window, and we also see that variational inference 4D var starts struggling in forecast mode. Now, if we look at the standard deviation, it's interesting to see that variational inference 4D var kind of produce the same pattern of, as ABC rejection sampling, and also in the forecast zone is kind of assessing high variance where the error are high, which is kind of satisfying. Now, if we can zoom at the coordinate level and plot some of the trajectories. So in the dotted line represent 4D var and the black line the truth. And for each algorithm, we have those different samples. So you can look at the behavior. One thing we can notice is that the ABC sample are well dispersed around the ground truth, while sometimes the ensemble member of the ensemble for the var with overfits or even variational inference for the var on average is a bit off. And also this point is kind of interesting, is that the variance during the optimization shrinks a lot. Overall, we can also notice that variational inference for the var and ABC produce similar shape. Those are same example, but on coordinate where 4D var is off from the ground truth, and you see that there is kind of a bimodal in the ensemble of 4D var, while the same remark can be applied for ABC and variational inference 4D var. Still, for instance, shrinking the variance here.
Arthur, you have 5 minutes.
Perfect, thank you. So finally, we can look also at the covariance evolving over time. So the first thing we can look is that, definitely variational inference 4D var kind of underestimate the variance here. And also a limitation that appears that the variational posterior we picked is not able to model covariance. So even though over time it seems like variational inference 4D var is catching up, but I don't have any quantitative metric to confirm this. I will finally give some perspective. So there is tool out there to perform variational inference with arbitrarily complex approximate posterior. And the idea is to transform a simple initial density applying sequence of invertible transformation, as you can see, for instance, in this paper. Another issue is the computational cost I mentioned earlier. So it's too expensive to optimize this loss function for every sample. And the machine learning community tackled this issue introducing what they call a recognition model, which is a model that will map the observation directly to the variational parameters. And I take this opportunity to advertise a papers of OR, where we kind of did the same thing, plugging a neural network before the initial condition, learning it on a data set, and training it directly on observation with the 4D var loss function. And finally, all I presented assume the dynamics perfectly known or perfect, which is not very realistic. But if you look at the weak constraint 4D var modeling, well, it seems that the variational frameworks fits also the same way, because what you do with constraint 4D is just introducing a more complex prior. And so the method naturally extend, but it also raised new questions. So how do we model this variational posterior? And I feel like it's related to simultaneous estimation of the states and covariance matrices. To conclude, if you have to take only one message home, is that you can optimize 4D cost over the variational parameter of a distribution instead of the initial condition. Also, I would like to remind that the results I've shown are only from one trajectory, which is not very satisfying. So you may want to try the code that is online now. And you also, if you feel like it tweaks some of the parameters, you can also find the slide at this address. And feel free to contact me if you want to discuss this. I will be happy. And thank you for your attention.
Okay, thank you, Arthur. That was very interesting. And you will find the questions that you can answer on Neopad, but I'll take advantage of my chair seat to ask you a question. So one of the criticisms that people make to 4D is that it assumes Gaussian errors for observation and prior. And if those errors are Gaussian, then you end up with a Gaussian posterior. And people see this as a limitation. So how does variational inference make things better if you already start assuming that your posterior is Gaussian?
Thank you for the question. Well, I assume that because it was very convenient and easy to code, but this is definitely not satisfying. And usually, and even when the observational error and the background error are actually Gaussian, the nonlinearity in the observation operator or the dynamical model will transform the posterior in a nonlinear manner, and it's not Gaussian anymore, even though the Gaussian assumption is right. But with those tools, normalizing flow, that you can start from a Gaussian and shape it exactly as you want. And I also feel like this is related to the hot topic right now in machine learning with diffusion model. It's like you shape the distribution. You don't shape the distribution yourself, but you can have arbitrary complex one.
Okay. Thank you, Arthur. It's been fascinating. And maybe if you can spend a bit of time on Neopad to answer the questions that our audience has asked you.
Of course.
So